Hello and welcome to the lecture Training of Recurrent Neural Network. In this lecture, we are going to understand backpropagation through time by which we train the recurrent neural network. Then we are going to see an example how character level modeling can be done through recurrent neural network. Then we study few deep RNN models. In today's lecture, we are going to discuss the training algorithm of simple RNN or recurrent neural network. As we have seen that recurrent neural network has this formation, that there is input x at a particular time instance and there is a weight matrix wx is associated with input. There is wh, that wh is another weight matrix. It is coming from the previous layer, the hidden input, and there is a output, that is wo, that is this wo is weight matrix of the output o. Now this particular structure, if you unfold it across multiple time steps, then it will coming like this, that for a particular state S1, x1 is the input, wx is the corresponding weight matrix, h0 is the hidden state input, and this O1 is the output, WO is the output matrix or weight matrix. Now for the S2, this H1 is being determined in S1 and go to the next state as a hidden input. You see S2 is H state T minus 1. So if it is a T, so T minus 1. So H1 is coming to S2 with the weight matrix WH. Similarly, X2 is the present input that is coming to this, that is with weight matrix WX, and the corresponding output is O2, the corresponding weight matrix W0 or WO, and this H2 is being determined by this. Now this is what we have discussed before. Now this BPTT training algorithm or backpropagation through time algorithm, which used for RNN, this network is unfolded across multiple time steps as we have discussed. So, and it will form a deep kind of computational graph kind of thing. Now it has two paths. This is the forward pass from time step 1, 2, 3, 4. So according to timeline, and this is another backward pass where error is propagated from final time step back through each preceding time step using the chain rule, as kind of similar in case of our special type of network like CNN. It is through the time instance, that was the hidden states. So here also the basic difference here is that there is a time involved here, and each time there is input is there, and previous state input is coming as an input to the next state along with this present of that particular time period, present input of that particular time period. So what we have seen, that during the forward pass, the hidden state is updated sequentially using the current input and the previous hidden state. So that this is the present input, this is the H1 is the previous hidden state input, and this allows this network to capture a temporal dependencies. This temporal dependencies means that how x1 x2 is somewhat related, or how x3 depends on x1 x2. how x4 depends on x1, x2, x3 and so on. This kind of dependency, this kind of relation, this is a temporal relation, and this temporal relation are being modeled by this kind of structure. Now, in backward pass, what is basically happening? The error, maybe it is a 4 state network. This is a final state if we just think. Now, this error is propagated from final time step back to each preceding time step using the chain rule. Now, there is a point that will come in our later slides, that the error is not only obtained at the final state, it may be obtained in the previous state also, if there is output. So, these errors at the different successive time steps we have to take into account. So, this is another kind of different uh, consideration in case of BPTT, that back propagation through time. That we will see how actually we, okay. So the error is being accumulated, and if you go from S4 to S1, this is one error, and for S4. I mean S3, this error these two error is being accumulated. O2, O2, O3, A4, 3 are accumulated. O1, O4, this O1, O2, O3, O4, and the corresponding error or error gradient is being accumulated. So that we have to take into consideration. Now, you see that the same weights are being used. Wx, Wh, Wo are all same. So same weights are shared across all time steps. The gradients computed at each steps are accumulated before updating the parameters in gradient descent orders. So what we have said, that this kind of consideration or setup is when it's back propagated, all these error gradients are taken into consideration. This BPTT or back propagation through time enables RNN to learn patterns in sequential data such as text, speech, time series sequence, etc. And now this our hypothetical example structure or RNN structure has RNN having 4 nodes, as t is equal to 4 with shared weights. Okay, so this is this. If we unroll time, this is 4 nodes. This is just a hypothetical example. And then we'll see how our BPTT algorithms are actually works. So in BPTT for a simple RNN, the major issue is that we have seen this is our basic architecture of 4 recurrent nodes. So these are the 4 nodes, and with shared weights, these are the shared weights. So the shared weights and a softmax output layer that is the output layer, and a cross entropy. We'll see in the next slide what is the cross entropy. So with this architecture, we try to understand our backpropagation through time, this algorithm. Now, with this setup, first we have to understand what is cross entropy loss. Now, L of t and is time step small t. This loss function O of t and xt. What is xt? This is xt, and this is output. So if these two are being given, so the cross entropy loss is basically minus xt of log of ot minus 1 minus xt log of 1 minus ot. So with respect to the input, that is the output, and the corresponding loss is being calculated by this. And one important understanding that the total loss is basically this L1 plus L2 plus L3 plus L4. So here L of y comma x, that means t is equal to 1 to t. So t is equal to what is 4. So LT of OT is t. That is our the cross entropy loss is defined in this way. Okay. Now here, what is the problem of that? As we know that a training algorithm for our deep learning model, any deep learning models, is that we have to determine these weights, this WGO, WH and WX. And by virtue of these losses, we take the error gradient, and this error gradient are being propagated through these states, in case these time steps, and we find these time steps from the chain rule, that what is the error gradient at this with respect to this L4 and other, and then we try to understand what will be the our WH2. So we use a weight updationer. So what is the basic idea here? Giving this loss across the time steps L1, L2, L3, L4, that we have to find out, or we have to update weight parameters, this Wx, Wh and Wo, using this back propagation through time process or algorithm. So that is the major. So we start our algorithm by finding that first Wo, because Wo is very easily, because it is the first layer. Okay. So we see the for back propagation it is required to compute the error gradient with respect to Wx, Wh and Wo with these weight parameters. So let's start with the Wo. Okay. Error gradient with Wo. That means what is error gradient WL? All these four of W. Now what does this mean? This is very straightforward, because this is the only way. This is what? L of t by del of LT by del of W, or L is equal to t to 1. This is summation of this. So WL of WO of this is just a summation of individual this error gradient at different levels at different time steps. Okay. So WL or WO, finding this is very straightforward. We just sum it up with t is equal to 1 to this t. Here t is equal to 4. So del of LT by del of W. Next come our WH. So next come our this WH. With respect to WH, del of L, del of H, or W of H, that we have. Now here there is a one situation. Now you could see, if you consider this S3. Now you see this S3 is being, there is a two error is involved. One is L4 and L3. For S2, three error is there, L2, L3, L4. S1 is all four errors are L1, L2, L3, L4. So you can see there is a two type of error. One is propagating error and one is the error coming for that particular state. That is basic difference between the CNN kind. That time the error is propagated through here from chain rule. But here the difference, or there is some difference in the derivation due to this two kind of error. One is coming from the presence error and other coming from the previous. So we can find W of L, which is W t is equal to 1, del of LT, del of WH, where t is equal to 1. That is its specific point. Now we have to find out this W of LT of WH. This del of L of del of WH can be obtained by summing gradient along the paths from L to WH. Now this L to WH, the corresponding WH is a particular. Now what is L4? Just you take the first thing, is WO into H4. It's very easy to understand. W, this L4, H4 minus O of T. That is the basic. This is the error, the L4. Now what is del of L4 WH? It is that if we just take a derivative of del L4 del of H, this is del of H4 L4 del of H4 into del of H4 by del. Just this is a chain rule, nothing else. Now what we have to find out this del H4 by del, this thing. Using chain rule, if we do some algebraic manipulation, and this, what we have to think about, this expression is coming taking into consideration of both. This is present input, present state, and the previous state. It is coming del of H4, del of Hi, del of Hi by del. So where I is equal to 1 to 4 is. So if this is this particular thing is this, that we can derive from this chain rule, so we can put it del of L4 del of WH is del of L4 by del of WH into this. Just we put it here in this equation. So in generic form with t time steps, we can write del of LT, this just we put a 4 is a t of del of WH is equal to del of LT, del of HT, and sum it of I is equal to 1 to t, del of HT, del of HI, del of HI by H. That is the basic this. So at every step we calculate this and we get these WH parameters. Now finally the error gradient with respect to Wx, del of x, del of Wx. Similar to del of Wt, del of Wh, we find this is also very similar because this is very the way it is affecting this Wx. So we can find d of Lt of del x is del of Lt of del of Ht, sum it up I is equal to t is equal to del of Ht. The only difference is we put it Wx here other than Wh. Otherwise these two are same. Basically this expression is same. Basically this will put Wx here. And for all t time steps we can sum it up over I is equal to t del of Lt of del of Wx, that we can find. So that is the only thing. So one thing we understand here, I just repeat it here, that this step S4, this is our final step. So only we consider L4 here. Okay, because this is coming L4. Now in this S3, there is the equations coming from this L3 and other. So L3, L3. This S2, it is coming L2, L3, L4. And this S1 is L1, L2, L3. It's coming. So there is two comments. One is present and another is from the total. So that is very important to understand. Here that how it is coming, the total loss, and we can find the derivative in this way. Okay. So this is the way that backpropagation through time for a simple RNN working. To summarize, in this BPTT algorithm for the simple RNN, this the main objective is to update the weight parameters Wx, Wh, W using this backpropagation algorithm. And to update these weights, we need to compute the error gradients with respect to weight parameter of this. And we have seen how we derive del of LT of del of WO, del of LT of del of H, and del of T with respect to del of Wx, where T is equal to 1 to T. Here, definitely T is equal to 4. Now, using this, we can easily update the weight parameters. This Wx, Wh, W is so this is the whole scenario of BPTT algorithm for simple RNN. Now we are going to understand what are the basic problems of backpropagation through time algorithm when used for simple RNN. Now here you can see that if there is a 15 sequence, okay, so that one this x1 to x15 and output is 01 to 15. So this is there, so many states or time instances there. Now one major problem, as we understand before, that vanishing gradient is one. That we'll see later how to handle it. And another problem is that they can't model longer sentence properly. So what does this mean? We'll come in this particular problem, long-term dependency issue or long distance word dependency issue in detail. But here we try to understand this, that let there is a sentence of with 15 words or something like that, and there is a one word here and one word here. So since there is a vanishing gradient problem, is propagating so many states or time instant. So this error gradient become very weak here, or very uh, reduced or close to zero here. So this output O2, this word, and O14, the relation, if there are two words are somehow related, this relation may not be modeled properly. So that's why RNN has a in general problem that it can't model the longer sentence properly. That is the major. We will see in detail this thing and how to solve this. So one kind of very simplistic solution of this kind of, when we are training this thing, that this, can we train a chunk by chunk? Let's say 1 to this 5, this step, this many steps or time instances. That this is the run forward and backward through chunks of the sequence instead of whole sequence. So these chunks we take 1 to 5. Now definitely when we training this particular sequence, the vanishing gradient problem will be less rather than the whole sequence, because it's a 15 sequence, now it's only 5 sequence. So if we train separately, then we can find that we can somewhat minimize the vanishing gradient. In the next step, we'll go for this carry hidden state forward in time forever, but only back propagate for some smaller number of steps. So now we are trained. This is already trained. Now we are training. Now this H5 is coming as an input to the previous hidden state, and we can train again this. So again, only this part will train at the time of training of time. So it back propagate is with this only. So the carry hidden state for infinite. So this is carrying from infinite states, from whatever previous. But all we are training or back propagating only this. It's output 10 to output 6. Another 5 seconds. And next step will go for O11 to O15. So another step. So it is coming. Whatever the state input, this or hidden input is coming. But this will back propagate only. So it will somewhat reduce the backpropagation, and this is called truncated backpropagation through time algorithm. That was one of the solution of the vanishing gradient problem. Now we are going to understand how this simple RNN model can be used to model some kind of application. For example, here a sequence to sequence model. Input a sequence and output another sequence. In general, this sequence to sequence model is of encoder decoder model. That means there is a one encoder part and one decoder part. So what essentially is encoder do? In general, encoder take some inputs and try to find some abstract representation or latent representation of these inputs, like here HD, which is basically the next hidden state of the final state of the encoder RNN. Now, what is decoder is doing? This decoder is basically taking this input and produce some outputs. Essentially, if we see that this encoder is many to one, so many inputs and one output, and decoder is one to many, that it take the one input and give many outputs. So that is now the basic structure, how a simple RNN thing can be used to make a sequence to sequence model. One is encoder part and one is decoder part. Now first with encoder part, this is many to one. That means it's several inputs and one output. Now this Wx is with x1. This is weight shared with all input different instance of time. X1 is coming first instant. In time instance 2, x2 is coming. Time instance 3, x3 is coming, and so on. Every time Wx is multiplied with it. Now from S1, this state, some previous input, maybe H0 is any. If there is no state, it's maybe some parameters of 0. This is We is basically the weight matrix for this. E for encoder. So with this H1, this H1 is the previous hidden input. This next S2 in the previous S2, the S3, and so on. From ST, the final state, HT of -1. This is coming from the previous state, and this Wx is coming from XT, and finally we get this HT. So HT is very important thing. In later study, you see, we say this is a context, or this is something very important, which is basically abstract or a kind of extract of all these inputs. Now this is given to the decoder. What is the decoder job? That decoder job is that to given this input. It basically generate some words that make another sequence. If there may be a sentence, these are the words, and this may be another sentence, this may be in other language or something like this. So here it is that this HT is coming with WD is basically the weight, because this is W encoder, W decoder, and W is basically this output 1, 2, 3. So essentially this is the encoder decoder structure, the sequence to sequence model. Now we try to understand how RNN based character level modeling can be done. It is, we know that our model is HT is tan H of WH in HT minus 1, that is weight matrix with the previous state input, WX with XT, the weight matrix WX with the present input, and YT is the output, this W into HT. That was our basic understanding from this diagram. At time step, XT is the our input with weight matrix WX, from HT minus 1 the previous state with matrix FWH. W is O is the weight matrix of the output, and the next state input is HT, that is state ST. Now there is a vocabulary. That vocabulary, how many these characters are involved? EAGR. They are, let's say, it's a very hypothetical example, and we first represent this. Then this is called one hot encoding, or kind of this. This E is 0001, A is 0010, G is 0100, R is 1000. So these are the 4 different ways to handle this EAGR, these 4 characters. What is our training sequence? Is the EGAR, this particular word. Now, what is our objective? That a RNN, how RNN is trained with this particular word EGAR, with these characters. Let's try to understand this. Now, this training phase, as we have discussed here, this is the input. This is the input character E, A, G, E, R, and something like that. These are input characters, and this is the input layer. E means 0001. That means A means 0010. G means 0100. E means 0001, and so on. Okay, and we use HTB that we have discussed. Now, see what happened. Now this WX is coming to this RNN node, with this WX it is coming, and WH is, that is hidden layer computation, that what is being done. After this computation, that is very much straightforward, that you can understand this. This is basically going to the output 0.7, 0.2, 2.51. These are the some values is coming here. Now you can see here that this is somewhat value. Now if we put it in softmax, it will come like this, that E is basically input character, which is input layer, then it is in hidden layer is coming, then this is output layer, this is, we put a softmax layer is 92. So 0010, this is A. So this is, now this is the testing phase. Now what happened? This A is going to the input to this, because please understand that this is the one input in output. So input are not there. So this output is become input. Okay. Now 0010, and then again it is coming to the hidden layer. We can find G. Now this G is what? 0100. You see, 0100 is our 100 our G. So that is the G. Okay. So that is the G. Now again this G is coming to the next state like this. And then again we can find this E. So E, A, G, E, and R, that is the target output. In this way, the basic RNN character level modeling That is the first criteria. Character level model. Now, character level embedding is a perform is one hot encoding that we have said that this is one hot encoding. Now, however, different embedding methods can also be used. So that is being done. Another important aspect, can we use this structure, is much deeper. It is the lengthwise. So another layer where we can put it there. So this is the one in RNN. This is the one, if you say this part is one RNN, and I put this is input to another RNN over this. So it's a deep RNN models. We can extend these models in this way. So one RNN model here, and that is another RNN, put it here. We can get much more. We can model much more complicated applications here. Okay. Another variants of RNN is called bidirectional RNN. As of now, what we have seen that RNN is basically working from left to right, from the instance of time from it is 1, 2, 3, 4 in this direction. So with this time direction. Now in bidirectional RNN, this RNN not only going to this forward pass, this with the time, it is also basically process the sequence in the backward direction also, to reverse the direction. So when it is coming into work or model some particular sentence, let there is an example, he went to bank to deposit money. Now you concentrate this bank. You don't know what is the meaning of bank. You can say bank of river, that also be a bank. Okay, but this bank is a financial institute. This thing is bit understandable to just see the is future or the later words. So in this case of understanding, this the future word or the later word is also going to help that what is the meaning of the actual sentence. So in bidirectional RNN, it processes a sentence in both the forward and backward direction, allowing it to use both past and future context at every time. Okay, so this helps to the model better understand the meaning of each element of the sequence, particularly in this kind of sentence or in this kind of application. So this is the this ST1, this is coming here, ST1 is coming. So YT minus ST and this is the forward, this is the forward path, this is the backward path. So here with EST as the future context, and this is the past context, and so this is the bidirection. So in this lecture, we basically try to understand the training procedure of RNN, that is back propagation through time. Then we try to understand the character level modeling through RNN, and then we try to understand few concepts of deeper RNN models like bidirectional. In the next lecture, we'll start LST. Thank you very much.